So we have dabbled into the world of carbonyl compounds for quite some time, and the only thing that we've talked about has been nomenclature. So at no point in time have we talked about reactions of the carbonyls. All right, so carbonyl, C double bond O, and there's something on either side of that carbonyl, and that is really what determined the type of carbonyl that we had. So let's take a look at what we have talked about so far, because we're going to have to be comfortable reacting with them now that we've named them. So one of the first was a carboxylic acid, and that was a C double bond O, and on one side we had an OH group. And then we talked about the acyl halides, and the acyl halides had a C double bond O with a halogen over on the right hand side. And then we had an acid anhydride. So an acid anhydride was basically this carbonyl that has a BFF of another carbonyl, and they hang out together through the mediator of an oxygen. The next one was an ester group, and an ester was a C double bond O with a oxygen on one side. And then we talked about an amide, which was a C double bond O with a nitrogen on one side, an NH2, an NHR, an NR2. It can be anything that you want it to be. And then the next one was a nitrile. And a nitrile is a carbon that's triple bond to a nitrogen. And again, you're probably saying, well, that's not a carbonyl. I know it's not a carbonyl, but it is part of the carbonyl family because we can use the nitrile groups in order to form carbonyl compounds. And that's why we talk about them now. So we have named every one of these groups so far. We've gotten comfortable with the IUPAC nomenclature. We've gotten comfortable with the common nomenclature. But we haven't spoke about reactions. Now, good news. Good news coming from this lecture. All of these functional groups, they all react in a similar way. That's why we group them together. There's other carbonyl compounds that are out there. Those react a different way. But the reason that we focus on this particular set is because this particular set does something very common when it concerns reactions that I want to do with them. So we learn how to name them, we learn how to use them, we learn how to recognize them, and we learn how to react with them all at one time. And that's why we set the lectures up the way that we do here, folks. All right? So overall, let's kind of talk about the general template. We have a carbon double bond O with a R group on one side of the house, right? I mean, we see a random alkyl group at least on one of these carbons. Well, I'm going to write it there. The other side, well, we're just going to write a Y. If it's an OH, it's a carboxylic acid. If it is a O, it's an ester. If it's an N, it's an amide. That Y piece will change depending on what type of carbonyl that I have. So if I'm pulling out of this group of compounds, the reactions have the same mechanism. Now, let's talk about mechanism. Let's talk about how this thing reacts and why it does what it does. So if I look at the carbonyl group, the C double bond O, it is a very nasty relationship. Oxygen is electronegative. Oxygen wants and wants and wants and wants and wants in that relationship. It's going to take everything that carbon has made and brought home, and oxygen's going to take it and run away. So the electronegativity value sucks the electrons toward the oxygen side of the house. And that creates a partial negative charge here. Now, keep in mind, oxygen is already surrounded by electrons, but it wants more, more, more. It's a little greedy. That's electronegativity. The carbon on the other side, though, the carbon just really can't put up for himself. I mean, you know, he can't take up for himself. He can't fight off the bullies. And this carbon, because of that, is going to be sucked of all of those electrons, and that carbon really doesn't have anything to share of his own anymore, so it becomes a partial positive. And we see this polarity somewhat type of difference between the carbonyl bond. Now, you know what's going to happen. You've already taken Chemistry 251. You already know the basics of the mechanism, meaning that if I bring in a nucleophile into the reaction, that nucleophile is going to carry a negative charge. That negative charge is going to look at this particular compound and say, ooh, hubba hubba, I see a positive charge. So we see an attraction that would happen right there. The nucleophile comes in, that nucleophile carries some negatives, it's going to look for positive areas of the molecule. If that carbonyl is present, that carbon is partial positive. They madly fall in love with each other. It's love at first sight, or just a drunken night on a Friday or Saturday at a club. And that carbon and that nucleophile form a new bond. But carbon says, wait a minute, I've got a bond to the left, I've got a bond to the right, I've got two up above. I can't be in a relationship with 5. You should only be in a relationship with 1. But whatever floats carbon's boat, I guess that's okay. So carbon is going to make this decision. I got to do something. I already have 4, and I want to take this extra one, but that will be number 5. So oxygen, you've been kind of needy and clingy the past couple of weeks. So you know what? You can just have these electrons. Ping, off they go. You can have them. I'm tired of it. Leave me alone. And when this begins to happen, we see a shift in what we would call maybe the transition state that happens in this reaction. So now what we have is a carbon that has shoved an extra set of electrons up to the oxygen, which makes this a full-blown negative charge, folks. Here we have the carbon now hooked up with the nucleophile that came in. It already had a bond to an alkyl group, and it already had a bond to one of these other pieces that we've talked about in the nomenclature. So this frees up carbon to have those 4 bonds again, and that's what it wants. That's what it wants. It's what it's always wanted, 4 bonds. And now here's our 4. But oxygen now gets the electrons. And it's not going to stay around like this for a very long time. Oxygen gets them, and then oxygen gets jealous. And it says, wait a minute. You brought this nucleophile in, and now you're paying extra attention to that nucleophile. And you think you should just pay me off? You think you should just give me the checkbook and let me go have fun and just not even really care about you? That's not the way this works. Maybe for some of you, you wish that was the way it worked. So oxygen's going to come around and say, no, I do not like this extra negative charge that I am carrying now. I would prefer to be neutral. I don't want this extra burden. So oxygen decides to take a pair of these electrons that carbon gave it in the first place and shove them back. It says, I'm here to stay. You're not going to kick me off. You're not going to throw me out to the curb. So I am back. This is my house. I live here too. And oxygen takes those electrons and it shoves them back to carbon. So now carbon's in a dilemma. And this carbon has to make up his mind or her mind on what he or she wants to do. Meaning, the carbon has to look at the 3 other bonds that are present. The R group, the nucleophile, and the Y group. And carbon has to make up his mind on which one to end it with. It tried oxygen. Oxygen wasn't happy, shoved him back. So now out of the R and the Y and the incoming nucleophile, carbon's got to make a decision on which one to cleave off. And in every one of these carbonyl compounds that we've talked about so far, in every one of them, this Y group is a very good leaving group. Oh, okay. This kind of is reminiscent of Chemistry 251 when we talked about substitution. And that's basically kind of what this is. We have an incoming nucleophile. That nucleophile has attacked the carbon of the carbonyl compound or the carbonyl functional group. The nucleophile attacked the partial positive carbon of the carbonyl. An electron shift happened toward the electronegative oxygen. The electronegative oxygen shoved those electrons back and said, no, that's not the way this is going to work. Carbon now makes a decision on which one is the better leaving group, and in every single one of the carbonyls that I have presented to you so far, that Y group is a very good leaving group. So carbon says, you know what? You're ugly. You're the best leaving group of all three. You're the ugliest of all three, and I don't want you around. So this bond, boink, those electrons go to the leaving group, and carbon and the rest of the molecule says bye-bye, bye-bye. That's what happens, and the leaving group goes away. The mechanism is the same no matter what type of leaving group that we have here. Now, without talking about ugliness, without talking about being greedy with money, let's kind of go back and look at this chart that you should have been presented with in Chemistry 251. And this is the substitution chart. This is a leaving group chart. And back in the substitution lectures, we said that some pieces of a molecule are prettier than others. We called those the nucleophiles. If a nucleophile comes into the picture, that nucleophile has prettiness assigned to it. And that prettiness is basically how it behaves as a base. So if you look at the types of groups that we've talked about, acyl halides, look at this, the iodine and the bromine and the chlorine. Those are acyl halides. Acyl halides are the ugliest of the ug. Those are going to be cleaved off of the molecule. They've always wanted to be cleaved off the molecule. Even back in 251 when we talked about substitution. Those leaving groups are ugly. The molecule does not want them around. And the reason is because they are the best leaving groups that are out there. Meaning that if they do leave the compound, iodine, bromine, chlorine, if they leave the molecule, they do not have a tendency to gain the proton back. They are perfectly okay on their own. They are perfectly okay being single. Now, in my opinion, they're single because they're ugly. Nobody wants them. But maybe in your opinion, they're single because they're independent. They don't need anybody. And that's the halogen group that we really start talking about. So what that means is that if I have an acyl halide, the acyl halides are going to be very reactive. And the reason they're very reactive is because they have the halogens, and the halogens are ugly, and the halogens are very good leaving groups, and the molecule can kick that leaving group to the curb. And it keeps the new nucleophile around, because I guarantee you that new nucleophile is going to be a prettier nucleophile than the ugly ones. It's the worst ones of them all. All right, well, another group that we talked about was a carbonyl with an oxygen, a C double bond O. Where is that? Look at this group right here, C double bond O. Right there it is. That's the ester group. Acyl halides are up at the top. Esters are down below. Well, esters are still a leaving group. They can still be kicked to the curb, but they're not as ugly as the halogens. So basically what that means is that esters are not as reactive as the acyl halides are. That group is a little bit prettier. Now, these other groups down below will beat it out. These are prettier than that ester group. But anything above this ester group on this chart, let's say alcohol, or let's say a water molecule, these are ugly. If I try to take water and react it with an ester, nothing's going to happen because water is uglier than the ester group and it doesn't want the water. It's going to say, nope, nope, sorry, I'm taken. I'm perfectly happy with my ester group. Water, you can go away. If I take alcohol and I try to react it with an ester, that alcohol is going to come in, and I almost guarantee you that that molecule will have its ester, and it will look at this alcohol, and it will say, oh, nope, sorry, no, you're a little uglier than the ester group. Go home. We don't want you around. We don't need you. We're all filled up here. Sorry, filled up. What's filled up? It's filled up. That's how these molecules behave. It's all about superficial, what's on the outside. And in chemistry land, folks, that's the assignment of a leaving group. Well, what else have we talked about? We've talked about maybe OR groups in the past. That's not really a carbonyl. This is just really an ether group, right? ROR. Well, where is that? Well, look down here. OR, right there. OR is even prettier. So that means ethers are going to be even more stubborn to react with than the esters. And the esters are more stubborn to react with than the acyl halides. And it's all due to the leaving groups. What else have we talked about? We've talked about alcohols. We've talked about OH groups. Right there they are. So if I take a look at the alcohol groups are even prettier. We started the semester off with alcohols. We've already said they are very hard to react with, and that's because they are not a very good leaving group. You have to make them ugly. We make them ugly by protonating them. But if I just take the OH group as it is, OH is much prettier than an ether, so alcohols are less reactive than ethers. Ethers are less reactive than esters. Esters are less reactive than acyl halides. That's what this chart is trying to get across. And finally, NH2, Miss America of the bunch. The prettiest one of them all. It's the Snow White of the leaving groups. It is the prettiest, which means that it is the number one group that will not be single for very long. That NH2 group, if it goes out and if it tries to be single, there are so many things that are swarming around that NH2, he or she will have to beat them off with a bat. Everybody wants in a relationship with NH2. Well, that's due to the leaving group nature. It is not a very good leaving group. It is a very strong base, which means if NH2 is out there, look at this, a 36, close to 40. If that NH2 is out there on its own and it's looking for something, it's going to find something to bond with because it is a very strong base. It is willing to accept anything and everything in order to get rid of that negative charge. Well, that is not a very good leaving group. Because if it does leave, it's going to go right back onto the molecule. Because it does not like to be single even for brief seconds, if it can help it. So amines are going to be less reactive than alcohols. Alcohols are less reactive than ethers. All of those we've talked about before. Ethers are going to be less reactive than esters. Esters are less reactive than acyl halides. Now you can see how the chart is starting to get put together. So anytime we have a group toward the top of this chart, that group is going to be a very good leaving group. Now, we have a special name for these types of reactions. If we bring in a nucleophile, well, organic chemists are not very creative. They call this a nucleophilic. Oh, go figure, we brought a nucleophile in. And that nucleophile is attacking the carbon of the carbonyl. Well, if you go back, we've kind of named this before. We've named this particular group. We've called that group an acyl group. Kind of common lingo a little bit. So we call this a nucleophilic acyl. And then that oxygen's going to push those electrons back. Carbon's got to figure out which one to push off. The nucleophile comes in, and if a reaction happens, that means it keeps the nucleophile. So if it keeps the nucleophile, something's got to leave. And we have a replacement here. A nucleophile comes in and replaces a group that was already there. Well, in other words, folks, that's called substitution. So this is another type of substitution reaction that we began to discuss in Chemistry 251. So these are called nucleophilic acyl substitution reactions. That's what we're getting ready to kind of embark on together. That's our journey. Nucleophilic acyl substitution reactions. A nucleophile comes in, attacks the acyl group. That carbon destroys the double bond. The oxygen reforms the double bond back, forming the carbonyl all over again, and then the carbon kicks a leaving group off so that way it can substitute the nucleophile for it. There you go. There's organic chemistry. It's kind of fancy sounding. But folks, if you understood what I just said, again, I think that you're learning. And like I've always said, learning is what matters in the very end anyway. So we're getting more comfortable with the idea of an organic chemistry reaction. That's what this is all about. All right? Okay, so now that we know the proper terminology, I also need you to understand that we can bring in a nucleophile. Depending on the carbonyl that we have, that nucleophile could, hey, can I buy you a drink, Carbon? And Carbon looks over and says, ew, no, I don't want you to buy me a drink, go away. And then, pew, that nucleophile is rejected. That can happen as well. And the way that that happens is it's based on the leaving group that is here. Carbon's going to look at the relationships that carbon is currently in. And if that nucleophile comes in and is uglier than any of those, especially that leaving group that we've identified, then carbon's not going to do anything. Carbon's going to be very content with what carbon has. And carbon's going to tell the nucleophile to take a hike. You're not getting my number. We don't need to pretend. We don't need to waste time. You just need to go bye-bye. And that nucleophile will go on to another molecule maybe and try to find its way there. But it will not react with the carbonyl if that carbon knows that the leaving group in question is prettier than the nucleophile. So once again, this chart, folks, it's going to be pretty important. This chart, again, I will give you. If you're taking tests in person, you get to use this chart. I don't want you to memorize this stuff. If you're taking a test online, well, you get to use it anyway, right? I mean, it's going to be right there. And I know that most people will use it no matter what. So I can't stop you from that. But this chart will always be available for you to use, no matter the format of the class. So if we go back and take a look at the carbonyls that we've talked about, that is why these things are ranked the way that they are. So acyl chlorides are the most reactive out of the bunch. We now know why. Chlorine, ugly. Ugly, ugly, ugly. Like I've always said, warts and, crookedness and deformed and nasty looking. It's like a witch at Halloween. That's what I look at the acyl halides as. They're witches of Halloween. Nobody wants it. Kick it to the curb and replace it with something else. If you get the opportunity, you better go with it. That's how this carbonyl functional group is going to look at that chloride. The next one is the acid anhydrides. The acid anhydrides are the OR groups, right? There is the O and the carbon double bonded O. They come next in line. Those are leaving groups. They can be kicked from the molecule, but they're not as ugly as chlorine and bromines. But the molecule doesn't feel bad when it kicks them out. Next ones are the OR groups. That OR group was basically this ether type of functional group that we talked about on the chart, and that is your ester. So esters are going to be more stubborn than acid anhydrides, and acid anhydrides are more stubborn than your acyl chlorides as far as reactivity goes. The next one are the OH groups. Again, that would be the leaving group is the OH group. And we know that kind of goes down to the bottom of that chart. It's very pretty. It's a very good base. So this one's going to be even more stubborn to react than esters, which are more stubborn to react than anhydrides, which are more stubborn to react than acyl chlorides. And then finally, our last one are the Miss Americas of the bunch, and that's our NH2 groups. So that would be an amide. This amide molecule will be very stubborn, very hard to react with them. So the amides are going to stand their ground. Not too many things out there that can replace the NH2 group in a substitution reaction, but we still kind of lump them into here. So amides are very, very stubborn. They do not want to react, and carboxylic acids can react a little bit easier, and esters can be reacted with a little bit easier than that, and then anhydrides are easier to work with and to use and to react with, and then acyl chlorides come next. There's the ranking, folks. There's the ranking of what we would call the reactivities of these carboxylic acid derivatives. And now you know why the order is there. It's all based on the chart. It's all based on the base action that they have. So, I kind of alluded to the fact that prettiness matters. I kind of want to give you an example before we start talking about reactions here. Let's say that we have a carbonyl, and we just have a random alkyl group over here. It can be anything that it wants to be, and a OCH3. Let's say that we bring chlorine in to the picture, and I ask you on a test, or I ask you on a quiz, hey, this chlorine is going to come in and react with this molecule. What kind of product is going to get formed? You better not let me trick you, because these are some of the questions that they will ask. So if you take a look at that molecule and you react that with chloride, this is what you need to think of. Okay, well, chloride's a nucleophile. That nucleophile is a negative charge. So if I wanted to kind of schematic out the mechanism, I could. There it goes. It's going to be attracted to that carbon. The reason it's attracted to that carbon is because this carbon is partially positive, this oxygen's partially negative, and there is an electron distribution that happens here where oxygen is more electronegative than carbon. So because of that, carbon's going to say, hey, we got a nucleophile. Here's my chance. I can get rid of an ugly one. And in order to do that, oxygen, you want the electrons anyway. I want you to leave me alone. And there you go. You can have them. And then oxygen says, no, that's not how this is going to work, because I don't want this extra responsibility of the negative charge. So whoop, there it goes. I'm pushing them back. And carbon says, well, shoot. I'm back to square one. But now I've got this chlorine. And this chlorine is on here as well as the R group and as well as the OCH3. So I've got to get rid of the ugliest group possible. And it looks at these groups, these choices, and it really is deciding between the OCH3 and the Cl. And if you go back to the chart that I just showed you, that's going to be listed into the Blackboard account, folks, this chart has chlorine way up here. Ugly, ugly, ugly. And then, what kind of group are we using? Well, we're using an OCH3 group. And the OR group, well, folks, it's down below. It's down below. It's right here, OCH3. That's the OR group. I don't know about you, but carbon's going to look at this and say, I've got OR right now, and chlorine's trying to make a move on me. And out of these two, chlorine's pretty trashy and ugly, and I don't want anything to do with it. So the molecule stops, and it does not allow chlorine to react. And the reason is because chlorine is a better leaving group. Chlorine is much better on its own than the OCH3 group is. And here is a case where if we have this molecule, which is a ester, and we react this with a halide, we will end up getting a no reaction that goes on. That is some of the stuff that we're going to have to walk through. Now look, this is just esters. This is the first kind of reaction using a carbonyl that we've named in this kind of module. But you know how many we've named. You know how many functional groups that we've talked about. And you can kind of imagine the reactions that are just going to start raining on the top of your head at this point. And that's what we're going to do in the next video. So we're going to take baby steps. We're going to go through this little bits at a time, making sure that we understand why things are reacting, why things are not reacting, and so forth. But this is the general mechanism that you need to learn. Because if you've learned the mechanism, then you can solve all of these little organic puzzles that I throw your way. But you have to understand what the mechanism is doing, meaning that a nucleophile will come in every single time. The double bond will be shoved up, then the double bond will be shoved back. Carbon will then look at the group that it currently has and the group that is coming in, and then that carbon will make up his or her mind on what they want to do. Do you keep what you had, or do you replace it with the nucleophile that came into the picture? And that is the nucleophilic acyl substitution mechanism. All right, so in the next video, that's where we'll pick up, and we'll start looking at these reactions, and we'll start maybe going back and naming things as well once we start doing real examples.